Welcome back, Math 10 YouTubers. Mr. Tronis here. We're going to do 2.3 here, factors of whole numbers. We're going to learn how to break numbers apart using a lot of skills we already have. So let's dive into it. What the heck is a factor? Well, factor is a number that when multiplied with another, it produces a given number, and that's called a, side note, that's a product. Okay, so factors always come in pairs. So we're going to set up a little bit of a t-chart. It's saying, what are all the positive factors of 60? Now, of course, there are negative ones, but we're going to ignore those in this case. And so what numbers multiply with 60? So start with the lowest possible factor that I can think of, which is the most lowest positive would be 1. And 1 times what gives me 60? Well, 60. And let's go to 2. Does 2 work? Does 2 times some other positive factor give me 60? Well, yeah, 2 times 30. And we can continue in this fashion. 3 times 20, 4 times 15, 5 times 12, and 6 times 10. And we notice now, if I go anywhere in between, you can notice that these numbers are going down, these numbers are going up. If I try 7, 7 doesn't divide into 60 evenly, 8 doesn't, 9 doesn't, and so I'm up to 10, so I know I found all my factors starting at 1 all the way up to 60. And so if I were to write the answer here, really simply put, what are the positive factors of 60? I would just list these from lowest to highest. So 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. And all of these, also remember, because they are factors of 60, means 60 is divisible by all of these. 60 is divisible by these numbers. It's saying the exact same thing. So remember our divisibility rules last time? Those help us to find these factors quickly. So if you remember some of those, it would help us to find 2, 3, 4, 5, and 6 really fast with all of these. All right. What about a unique thing called a prime number? You've probably heard of these before. They are really, really important. They are essentially a whole numbers whose factors are only 1 and itself, meaning it only has 2 factors, 1 and itself. Like for 60, it'd be 1 and 60. But 60 is not prime because it has 2 times 30, 3 times 20. So a prime only has 1 in itself. So the very first prime, if I were to list them in order, is 2. A little side note here, some students think, but 1 is not considered prime. Okay, it has to have 2 unique factors, and one's only factor technically is 1. So 2 is the very first prime because it's only divisible by 1 and 2, then 3, then 5 because 4 is divisible by 2, so that doesn't work. Then we have 7, 11, and so on. You can keep going, 13, 17, 19, 23, etc. They get a little harder after that. So we actually have a method, and something really unique, which is really cool about our positive whole numbers, is we can do prime factorizations of any positive integer, okay, any positive integer except for 1. So 2 all the way to infinity, and we can break them apart by finding all of the prime numbers that multiply together to make the given number. What's kind of cool is this, except 1, of course, can be broken down into prime factors. And prime numbers are really important, especially with all of your phones and everything you use in technology, because that involves encryption or cryptography, because you don't want, you want your bank account protected when you're using it to to tap or to use it with debit machines and send it over radio waves and so on and so forth. So the idea is it takes computers a really long time to prime factorize these really large numbers. And I'll talk a little bit more of that in class because it's a really cool application of prime numbers. But let's see how they actually build every positive number to infinity. Well, let's take a few examples here. And we're going to do a prime factorization tree. So we call these, in short, just factor trees. And they're really easy once you get the hang of it. So if I take 90, I can break it into two factors. And you can pick any two numbers that multiply to 90. Because I know 90 is actually divisible by 30 times 3. So I see that, I'm like, yep, it's divisible by 30 and 3. And then I look at, okay, of these numbers, are they prime? Can I divide them by anything? Well, the 3, okay, is prime. It's one of our lowest primes, but 30 is not. It can be broken up into more factors. I can break it up into 5 times 6. Well, 5 is prime, but 6 is not. 6 can be broken down into two more primes of 2 times 3. So I'm taking each branch of this tree and breaking it down into factors until I get to primes. Once I have all primes at the end of my branches, I'm done. So the way to represent this is 90 is equal to, and I can break it into these primes being multiplied or to create the product of 90. So I take my lowest prime, which is 2, and I multiply it by 3, and then I multiply by another 3, and then by 5. And you could try this in your calculator. 2 times 3 is 6. 6 times 3 is 18. 18 times 5 is 90. We usually write it in a shorter form of 2 times 3 squared times 5 because we know that I can represent 3 times 3 as 3 squared. So use exponents where you can. All right, let's do a bigger number like 400. So first, I see this ends in 2 zeros. So I'm going to break it up into 4 times 100. I look at my 4, I know that's not prime, but I'll break it into 2 times 2, so I know I'm done there. 100 is definitely not prime, so I'm going to break that into 5 times 20. And then again, I could do it in multiple different ways. I'm going to take 20 and break that into 5 times 4, and then 4 is not prime. I'm going to break that into 2 times 2. And we can see, what do I have left? If I check all my numbers, yep, 2, 2, 5, 5, and 2 more 2s, those are all primes. So I'm ready to write my prime factorization, which is 2 times 2 times 2 times 2 times 5 times 5. But that's a long way of doing it. Let's use our exponents, which is 2 to the 4 times 5 to the 2. All right, two factor trees done. Let's do an even bigger number like 3,300. Now, again, ending in 2 zeros tells me it's divisible by 100, so I'm going to do exactly that. If I can start with bigger numbers, that's even better. Okay, I could have divided this by 2 or by 5, by 3, but it doesn't matter which factors you start with. You just look at each of them and say, okay, is 33 prime? Well, it's definitely not because it has 3 times 11. But I'm actually done here now because 3 is prime and so is 11. So those two branches I can move away from. They are prime. I can deal with the 100, which we just did above. So I'm going to show what I did here. Remember, I broke it into 5 times 20. Let's change it up and let's change it to 2 times 50. Okay, maybe you can't think of 5 times 20, so you have to start lower with 2 times 50. Well, 2 is prime. I'll split apart 50, and I know that's divisible by 2 as well. Whoops. Um, do 2 times 25. 2 is prime, but 25 is not. That can break into 5 times 5. And now I have all of my primes. And notice I get the same 4 primes with 100. Here I got 5522, and here I get 2255. Exact same result. So let's write it out again, but I'm going to combine all my consecutive. So 2 and 2 is going to give me 2 squared. I have 1 3, so that's times 3. I have 2 5s here, so that's times 5 squared. Let's put a little dot there. And finally, I have an 11. And there's the prime factorization for 3,300, which is what we can start to see is you could probably notice that if I had really huge, like 100-digit numbers, it would be really hard to find prime factors of that. We'd need a computer. And that's exactly how encryption works. Again, I'll talk more about that in class. So let's move on to the next page here and see an application of this. GCF you have heard of before. That stands for the greatest common factor. Well, common what? Well, common factor between two numbers. Okay, so greatest common factor. So we can use these prime factor trees to find a GCF really fast. So it is, again, the largest number that divides both of the given numbers. Sometimes we can do that with mental math if we're strong enough in that area. But if we have bigger numbers, that gets tougher and tougher. So let's do a couple factor trees here to find our GCF. Um, so uh, first, let's take 80. Let's do it right here. And right away ends in a 0, so I know it's divisible by 10. So I'm going to break that into an 8 and a 10. And 8's not prime. I'm going to break that into 2 and 4. And that breaks into 2 times 2. 10 breaks into 2 times 5. And I have my prime factorization. Prime factorization of 80 is 2 to the 4 times 5. Okay, and again, that's coming from, I have 1, 2, 3, 4 2's and the 1 5 being multiplied. Now let's take 96 over here and let's do a prime factorization of that. It ends in a 6, so I know it's divisible by 2, so let's do that first. So that's going to be 2 times 48. Okay, 2 is prime, but 48 isn't. I'm going to break that apart. 48 has, again, it's divisible by 2. So I'm going to get 2 times 24. 2 is prime. 24 is 2 times 12. And then see the pattern of the 2's. 2 times 6. And finally, 2 times 3. So in this case, I get how many 2's? Let's make sure we're careful counting them. 1, 2, 3, 4, 5 2's. So I get 2 to the 5 and the 1, 3 left over. Okay, well, how can I use a factor tree to figure out the GCF? Well, it's the exact same thing. Let's compare these two. I'm finding the greatest common factor, which is the same as finding, we're going to see it down here, for large numbers, we can do a factor tree for each and collect all of the prime factors that are in common. So find all the pieces in common. So let's write it here. So 80, and I'm going to write it out the long way to show it, 2 times 2 times 2 times 2 times 5. And 96 is equal to 2 times 2 times 2 times 2 times 2 times 3. And let's find our common factors. We're just making matches. So I have 1 pair of 2's, 2 pair of 2's in common, 3 pairs of 2's in common, 4 pairs of 2's in common. And now this 2 and 3 have no friends up here. This 5 has no friends down here. So I have 4 2's in common. That tells me that the GCF is going to be equal to 2 times 2 times 2 times 2, 4 2's together, which is 2 to the 4, which is the exact same thing as 16. And you could test this out. They are both divisible by 16, and that is our greatest common factor because it is the common prime factors being combined. Okay, let's try it with 2 more examples, and we'll be done this set of notes. So first, let's do a prime factorization of 102. So I'm going to go a little faster with this stuff. 102 ends in a 2, so I know it's 2 times 51. And 51 may look prime, but it isn't. If you add those digits, 5 plus 1 is 6. That means it's divisible by 3, which is 3 times 17. It's one of those tougher ones that look prime, but it's not. So 102, we have our prime factorization. You can underline or circle them. So there's 2, 3, and 17. And let's do 114. We're going to split that into 2 times 57. And then 57 is not prime either. It is divisible by 3 because 5 plus 7 is 12. You can see why divisibility by 3 is handy. Times 19, and 19 is prime. So we have 2 and 3 and 19. So now we just do a quick comparison. Let's lay out both of our prime factorizations. So 102 is equal to 2 times 3 times 17, and 114 is equal to 2 times 3 times 19. And all we got to do is find our common primes, which is 2 and 2, 3 and 3, and multiply those together to get our GCF. So our GCF is equal to 2 times 3, which is 6 in this case. All right, one more and we'll be done. First one here is 162. That is divisible by 2, but it's actually, if we add these digits, 1 plus 6 plus 2, we get 9. It means it's divisible by 9. So it's better to start with something bigger if we can. And in our calculator, will tell us that 162 divided by 9 is 18. If you can't do that in your head, let's break these apart into their primes. So I get 3 and 6, and then 6 breaks into 2 and 3. So there's our prime factorization there. I have 1, 2, 3, 4 threes and 1, 2. And let's do 306. 306 is divisible by 9 as well, because 3 plus 0 plus 6 is 9. So that's 9 times 34. Again, 9 breaks into 3 times 3. 34 breaks into 17 times 2, which are both prime as well. So we again have 3, 3, a 2, and a 17 for our prime factorization. So let's list them right beside each other or above and below so we can easily find our pairs. This one has 1, 2, and then 4 threes. And 306 is equal to 2 times 3 times 3 times 17. And we just find our matching pairs here. So we have a pair right here, 2 and 2, 3 and 3, 3 and 3. So there's our GCF. We just got to multiply the 3 common primes, which is 2 times 3 times 3, which is going to give us 18, and we are done. That is our GCF. All right, Math 10s, we'll see you in class. Have a good one.